heat required when 12 moles of propane is heated from 250 degrees Celsius to 1200 degrees Celsius at approximately atmospheric pressure in a steady flow heat exchanger. First, assume ideal gas. You are given both the initial and final temperatures in degrees Celsius. Convert the initial temperature to degrees Kelvin. Likewise, convert the ending temperature to degrees Kelvin. Replace the temperature values in Celsius to temperature values in Kelvin. Find the ratio of final temperature divided by initial temperature, which equals 2.8159. Start with the ICPH function because of the assumption of ideal gas. Here is a table for heat capacities of gases in the ideal gas state. Select the values for propane. Note that the B value needs to be multiplied by 10 to the negative 3 power and the C value needs to be multiplied by 10 to the negative 6 power. From the table, the values for A, B, and C are in the upper right in purple. The tau variable is the ratio of the final temperature over the initial temperature. This value plugs into all three parts of the function. Likewise, the initial temperature plugs into all three parts of the function. Finally, the values from the table can be inserted into the function. Let's solve the function one part at a time. Here is the first part. Plug in the known values. This part of the function equals 1152.34. Let's look at the second part of the function. Plug in the known values. The value this part equals 27,289.94. Finally, let's look at the third part of the function. Plug in the known values. The third part of the function equals negative 8,981.94. Add these values together. These values added together equals 19,460.34. The value of the complete function is 19,460.34 Kelvin. Change in enthalpy equals the ideal gas constant times the derived value from the ICPH function. You have the derived value from the ICPH function. Because of the assumption of ideal gas, the ideal gas constant can be used, which is 8.314 joules per Kelvin mole. This can be inserted into the enthalpy equation. Enthalpy equals 8.314 joules per Kelvin mole times 19,460.34 Kelvin. Kelvin values cancel each other out. The change in enthalpy equals 161,793.267 joules per mole. The change in enthalpy also equals 161.793267 kilojoules per mole. Heat equals moles times the change in enthalpy. You have the value for both moles and change in enthalpy. Plugging in these values into the heat equation yields the heat required to be equal to 1941.5 kilojoules. This is the final answer for the problem. Great job, you are improving your understanding of thermodynamics. If you found this video helpful, please subscribe, like, comment, and share. Please check out other videos on this channel. Thank you for watching.